All right, a couple of announcements. Two are general kind of announcements and one specific for this course. First, if you have been looking for, I doubt if any of you have, but if you have been looking for me, Tuesday and Thursday afternoons about the only time I have, Tuesday and Thursday from 10:45 until 4:30, it was listed as about my only major times of office hours. Well, for the last couple of weeks, and it's going to continue through this week and into next week, okay? I've had to go over to the Birmingham campus just about every Tuesday and Thursday afternoon. What I'm trying to do is get all my annual evaluations completed, and most of the instructors are over there. I've got one more over there who I haven't been able to catch for weeks now, but he's supposed to be there today. And also I've got one that's supposed to send me one on the email. I'll have to check into that tomorrow. I don't have time today. But anyway, I've got to go over and take care of those things tomorrow. So tomorrow I'll be leaving here probably around 2, maybe a little later, but I won't be here till 4:30 like the thing says. Then on Thursday, we got a meeting over there at 2:30, so I'll be leaving here around 2 to get over there by the meeting at 2:30. Okay? Then Tuesday of next week, we have the planning hearing, which is what the meeting's about coming up, and I can't remember what time that is. It may be a little later in the afternoon, but still I'll be over there for part of the afternoon, whereas normally I have office hours. But after Tuesday of next week, I'm hoping all the mess over on the Birmingham campus will be finished, so from Thursday on, I'll be back on regular office hours. So that's one thing I wanted to make sure you understood. All this other stuff is also hindering my getting grading done, and I've just gotten a pile of papers in today, and I have some left over that I didn't get finished over the weekend, so I'm going to have to be trying to juggle those in between. And here's gold. All right, so, and I'm way behind on Blackboard, as if anyone's noticed. I'm way behind on Blackboard. I hope to get that caught up sometime soon, too. We've been out of town the last 2 weekends. This weekend we'll be in town. I don't know, got so much work to do at home that since we've been out of town, I don't know if I have time to get stuff done, but I'll try to. Okay. Next thing is student course evaluations. Have any of you started them yet? Oh, you have, okay. Any finished them yet? No, not finished? Okay. Oh, you have. How? Oh, yeah.
My computer gets locked right after I finish the first question. It locks up there, and I can't get any further.
Okay. Okay. Check with them, or possibly, yeah. You know the person down there, first floor? Okay. They may actually have a computer you can sit down and do it at. If they don't, possibly the library computers or something. Yeah, okay. That might work, because they should work. Now, they're not due immediately. You can wait till the very end of the term and see that final exam, final grade if you want to, but please don't forget to do them. They close it out on the 8th of August. Now, that's long after the term's over with. Don't wait till that long to do it. You're going to, or if you're anything like me, you're going to forget it by then. So please get those done. Yeah.
Where do you go to?
Okay. The easiest, have you gotten onto your Lawson email at all? You have? Okay. You'll find probably 2 emails there about them, maybe more. And on the email, there'll be a link. Click on the link, you're there. Okay. Now, if you can't get your Lawson email, I can tell you another way to get there. But can you get there that way? Get there. All right. That's the easiest way to do it. I'm all for easy. All right. All right. Now, the next announcement has to do with what we were going to be doing. I had said last time we'd just do a quick PowerPoint show of 9.8. When I just tried to load at the end of my last class, when I was trying to get things done for it, I tried to load 9.8, and there must be some problem in the file is corrupted, and they said if they try to correct it, it may damage my computer. And since it was just going to be a slideshow anyway, we're not doing 9.8. Okay, you weren't going to be responsible for it anyway. But in 9.8, there was a little blurb there on James Gregory. And he was one of the earliest mathematicians to work with power series. He was a Scotsman, James Gregory, developed the power series method for interpolating table values, a method that was later used by Brooke Taylor that we just talked about in the Taylor series. So all these guys interacted, if not in person, by concepts anyway. So then today we're going to be starting at 9.9 because 9.8 the PowerPoint won't open. And again, you're not responsible for this on the test, but I did want you to be able to recognize it if you ever need it. Okay? So continue in Chapter 9, Infinite Series. Any questions before we get started on this? Again, this is going to be a quick PowerPoint show with the representation of functions by power series, as if we haven't been doing that for a while now. But the objectives here are to find the geometric power series that represents any old function. Okay? And then we'll do constructor power series using series operations. Now, there's a guy featured here on page 661 of our text. Whether you got it or not, you can still use him. His name is Joseph Fourier, is how I think it's pronounced. French, obviously. Some of the early work in representing functions by power series was done by the French mathematician Joseph Fourier. His work was important in the history of calculus, partly because it forced 18th century mathematicians to question the then prevailing narrow concept of a function. Both Cauchy and Dirichlet, I guess is how, were motivated by Fourier's work with series, and in 7 years after Fourier's death, Dirichlet published a general definition of function that's used today. Now, Fourier is most known for a series named after him. It's the Fourier series, and it involves sines and cosines. We're not going to get into that particularly here, but that's what he's very well known for. He's still a pretty interesting character. If you notice the years of his life, 1768 to 1830. And if you think about some of the things that happened in that time frame, of course he was French, but in that time frame, when he was born, I'm trying to think, I guess we had 13 colonies by then. I think Georgia was founded around 1735 or something like that. So we went from being 13 colonies to an independent country to operating under a confederacy that didn't work too well, that then changed to a federal system. But about the same time we were going through all that, France underwent its own revolution. In fact, in many ways, some of the French thinkers influenced the American Revolution, and America's success in overthrowing Britain encouraged the French to try to overthrow their monarchy, which they did, but they were not nearly as successful. Theirs was one bloody mess, okay? It was a pretty awful time in French history. Joseph Fourier was involved with some of that. After the monarchy was defeated, they tried sort of a constitutional government for a while. It didn't seem to work very well. And along came a little guy named Napoleon. And I think Fourier was, may have been an officer, but at least a consultant or something in Napoleon's government. So, an interesting character. A lot went on in his lifetime. If anyone's interested in him as a paper topic, I think you'll find him a very interesting character. I'm not going to say Fourier's series are all that interesting, but he was a pretty interesting character. All right, so let's go back or pick up again. Geometric power series. Consider the function given by f of x is 1 over 1 minus x. The form of f, that function, closely resembles the sum of a geometric series. If you remember the sum of a geometric series, the summation n equals 0 to infinity, a to the r to the m, r to the n. As long as the absolute value of r was less than 1, then this was a converging series, and it converged to this value, a over 1 minus r. Well, that looks pretty close to here. Factor of a, put that in front of it, and you've got this right here. So in other words, when a is equal to 1 and r is equal to x, okay, what we have here is a power series representation for this function right here. Centered at 0, 1 over 1 minus x, okay, is equal to this right here, as long as the r is less than, the absolute value of r is less than 1. Okay? Now, so, if a is 1, then this is the same as the summation n equals 0 to infinity of r is equal to x, x to the n. So this is 1 plus x squared plus x cubed plus x squared. That's what you're doing. As long as the absolute value of x is less than 1, just like here we require absolute value of r is less than 1, there's your power series. Okay? And this function is represented by exactly that power series when a is equal to 1. Okay. Of course, that series represents f of x equal 1 over 1 minus x only on the interval from minus 1 to 1. Why? Number 1, remember we said, yeah, x had to be less than, absolute value of x less than 1, so it had to be between there. What's even more, it can't be 1, because then you'd have 0 in the denominator, just like you said. So basically, to represent f on another interval, you must develop a different series. So this one's true for here. That one's true here. To get this half of the same function, okay, no, I'm sorry. Yeah. Okay, back off a minute. Get this reversed. This is a function, f of x equal 1 minus x, okay? Obviously, no value here, okay? But this only represents, the power function on the previous slide only represents this portion here. X is between minus 1 and 1, okay? The power series only works there. In fact, this is its illustration here, that part. To get this part down here, no way you can get it with the power series unless you do some manipulation. To represent f in another interval, like over there, you have to develop a different series, okay? And obviously it would have to be a negative series because everything's negative there, but it would be quite different. So that's only good. This is f of x 1 over x, okay? 1 over 1 minus x. This part here is the only part that's represented by the power series, okay? Because that's very limited, okay? Now, so for instance, to obtain the power series centered at minus 1, what you have to do then is well, you not responsible for this, so I don't want to spend too much time focusing on how they went about doing this. They're doing a whole bunch of manipulation with the numbers. And basically, well, without doing it, you can monkey around with this and represent it by this one, which actually turns out into that power series, which implies that your A is 1/2 and R is that. But again, this thing has to be less than or equal to 1. The absolute value of that less than 1. And it goes on. So it's going to take too long to go over all this, but you can read the book or go to the website and probably be able to follow it. So we're not going to do much of this. Let's just cut sort of to the chase here. And again, I'm not sure you're going to run into much of this. If you do, you'll probably need to go back and you'll probably have to have course in this that's more specific. Here are some of the operations with power series. The one place that we've got a problem here is section 9.8, which introduced the power series. I can't show you the slides for because that file was corrupted. So we can't go into all this. So I think this is probably going to be almost, I don't want to say worthless, but I'll just point this out to you. If f of x is some power series here, g of x is some different power series there, okay, then the linear operations, f of k times x would just be k times the summation. It doesn't quite work the same way. These are not linear operations. Remember, in most things, you just pull the k on the outside and say k times f of x. Not the case here. It's k to the n. So this isn't what we call a linear system, the power series. Okay? They don't even define what this is. So I'm not. Now this part is true. F plus or minus g is the summation of the sum. How to say this? The sum of two power series is the power series of the sums. Okay, that part is linear in its appearance. The constant multiple part is not. So just leave it like that. Okay. Okay. That was not worth much except talking about 4A, there's a 4A. Because we couldn't have, one other. Toward the end of this section, and I'm going to be terrible at pronouncing this. I wish Lal were here. He probably could tell us exactly who this is. Srinivasa Ramanujan. Okay? Latter part of the 19th century, early part of the 20th century. It doesn't say here, but I would bet you bottom dollar he was an Indian mathematician, and he it mentions here that series have been used to approximate pi, have interested mathematicians for the past 300 years. An amazing series for approximating 1 over pi, yeah, it does say he's Indian, was discovered by this guy, okay? So here's another potential paper topic, and there's also an article that refers to them, and there's another one on that same page that refers to 2 other methods for approximating pi. Looks like those are by, I'm guessing, a Chinese author. So there's plenty of things in that section that you might find of interest. Now, that wasn't much of a section. This, I think, is the last one. Let me see. Yes. Last one, but this is the one I wanted to get to just because these are the ones, believe it or not, you've used the most in your life, and you've never even realized it, probably. And these are Taylor and Maclaurin series. Now, we had Taylor polynomials and Maclaurin polynomials, and they are related, but this is a series, okay? If I can get this one to open up. 9.8 wouldn't. Let's see if 9.10 will. It doesn't look promising. But let's see what happens. Let's go to some current slide and see what happens. That doesn't look good, does it? But this does. 9.10 is Taylor and Maclaurin series. And we'll find Taylor and Maclaurin series for a function. At least you'll look at some. We'll find a binomial series, okay? And we'll use the basic list of Taylor series to find other Taylor series. We're not going to actually do that much with them, but I want you to see them and see how they're used. Because like I said, if you've ever operated a calculator and you told it to find the log of 2, use Taylor series. That converges, it converges rapidly, and that's what your calculator's doing. It's using a Taylor series to do that. My bet is, I'm not up with calculator technology, but I bet you they're still doing that. That's how they originally did it. I don't think anything's come up faster. So Taylor series and Maclaurin series. We'll study a general procedure for deriving the power series of a function that has derivatives of all orders. That's the requirement. The next theorem gives the form that every convergent power series must take. Every convergent power series must take. Form of a convergent power series. If f is represented by a power series, f of x is some summation of a sub n times x minus c raised to the n. As a power series, you usually say centered at c, but you don't have to call it that. It's s minus c raised to the nth power. For all x's on an open interval I containing c, so here's your interval, c is somewhere in that, then the coefficient there, a sub n, is your nth derivative of the function, f, that you're representing, evaluated at that value c, divided by n factorial. That's the requirement, okay? And then this f sub x, this thing will be represented by f of c, so first the function evaluated at c, times f prime of c, this first derivative is evaluated at c, times x minus c, plus f double prime over 2 factorial times x minus c squared. You go on down and you keep dividing your nth derivative evaluated at c divided by n factorial. Now remember, those n factorials grow really fast, okay? Give me a number, any number. Make up a number. 12? Okay, 12. 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. Try multiplying those out and see that is a huge number. 12 is not that big a number. It is an enormous number. 12 factorial, this term, no matter how big this is going to be, that's going to be overwhelming it in a while, okay? And the power here, that overwhelms it, you know. So that's why these things converge and converge rapidly, or at least an indication of why. Okay, the coefficients in the power series in Theorem 922 are precisely the coefficients of the Taylor polynomials for f and c. For that reason, the series is called the Taylor series. Okay, Taylor came up with the polynomials. I'm not sure he ever knew they'd be used in a series, but they named them after him because they used his polynomials in it. Okay, if a function f has derivatives of all orders at x equals c, then the series, the summation n equals 0 to infinity, the zeroth derivative is the function itself at c, Anyone remember what 0 factorial was?
1.
1, exactly. Okay, times x minus c to the 0th is just 1. Okay, so that term would just be f of n, f at c. Okay, and that's what it is right there. And then when the first derivative over 1 factorial, which is 1 also, x minus c, and then you just keep on going from there. That's called the Taylor series for f of c. Now, if that c happens to be 0, then the series is called the Maclaurin series for f. Because Maclaurin's polynomials were just like Taylor polynomials, except they were centered at 0, not at some arbitrary number c. So Taylor series are more general. Maclaurin series a bit more specific. So if this is your sin x, okay, f of x equals sin x, to form the Maclaurin series, it's of course going to be at 0 then. F of 0, well, sin of 0 is 0. F prime of 0, derivative of sine is derivative of sine is cosine, and cosine at 0 is 1, so that would just be x. So this would be 0, that would be x. Second derivative of sine, it's going to be a sine, it's going to be a minus sign, but who cares? At 0, it's going to be 0, so that one disappears. In fact, all the even derivatives are going to go to 0 because all the even derivatives of sine have sine in them, and evaluated 0 is 0. So you wind up, and then the odd ones are going to alternate SIGN signs. So this would be x plus minus x cubed over 6 plus, yeah, and it goes on with alternating these, plus 1 over 5 factorial, x to the 5th, minus 1 over 7 factorial, x to the 7th, and go on and on and on like that. Determine the interval for convergence. Well, we won't mess with that. But that's how you get the Maclaurin series for sine, if it's centered at 0. So if you take your substitute derivatives, the function itself is 0 at 0. Its derivative cosine is 1 at 0. The second derivative is minus sine, but it's going to be at 0 at 0. And you keep on going, the third derivative is minus cosine, and at 0 that'll be a minus 1. So they alternate signs, skipping every other term, by the way. So there you have another 0, and so on. Okay. The pattern repeats after the third derivative forever, so it's only the odd derivatives that give you a value. So this is going to be, as you write it, difficult to determine. But this is going to be 0, that one's 0, that one's 0. So by the time you do take all that into account, okay, you've got the every other one is 0, and every other one that's not 0 changes sign, SIGN sign. And so you get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And this is how your calculator determines a sine function. When you punch that in and do sine of, and these are in, by the way, radians. The x's here are radians, okay? Don't think that's going to work for degrees. You have to do manipulations to get up to the degrees. This will give you radian. That's exactly what it does. You plug in a value, and it's going to give you, do this series, and it will converge, and converge very quickly. Okay? And there is the summation representation of that, because every other term is changing sign. You have a minus 1 to the nth. So when n is 0, it's positive. and that's where it starts at 0. When n is even is positive, and is odd is negative. Okay? X to the 2n plus 1, of course, when n is 0, that would be x to the 1, so there's your x. And when the next one would be, you're doing only the odd powers for x. And then you do that same number here as a factorial. So that's how you write that term. Now, by the way, we mentioned Maclaurin series. There's a little blurb on Colin Maclaurin, another I'm pretty sure Scottish. I just can't. No, I'm sorry. I think he was Irish. No, Scottish. That sounds so Scottish. Okay. But in this little blurb about him, it mentions Gregory, Newton, John and James Bernoulli. They were the brothers. Leibniz, Euler, Lagrange, Wallis, Fourier, all contributed. However, the two names that are most commonly associated with power series are Taylor and Maclaurin. So, plenty of potential paper topics there. Okay. And that converges for all values x. Okay? All values x. Notice we chose the Maclaurin series because it was centered at 0, but it will work for every value of x, all values of x. Okay, so don't let that centering at 0 tie you down too much. But then, okay, it says here, by the ratio test, you can conclude that this series converges for all x. You cannot conclude that the power series converges to, the series converges, but does the power series converge to sine x for all x? You can simply conclude that the power series converges to some function. You're not sure what it is. That's a subtle but important point dealing with Taylor and Maclaurin series. So we won't get into these subtle points. Okay. So this is one of those subtle points. All right. So this shows you some of the limitations of the Taylor and Maclaurin series. But since we're not going into it, let's not get too bogged down with it. So here's theorem 919. The function f is differentiable through order n plus 1 on any interval I containing some number c, then for each x in that I, there exists z between x and c such that, goodness gracious. Now this is Taylor's theorem. So going back to Taylor. There's the z. I was trying to think, where in the world does the z show up here? It shows up in here. The r sub n I think this is probably beyond what you really need to know here, but this is Taylor's theorem. Okay, got it. These are the terms in the Taylor series, but there's somewhere out there, there's the r sub n, because remember, the function is only differentiable through order n plus 1. So once you get up to f sub n, you really can't go much further. The next term, the r sub n, that's a remainder, is going to separate f of x from this series. Okay? It's going to be this, and that remainder term depends on that n plus first derivative, and that may be the last one that you have, evaluated at some value c in between x and c, z between x and c, and this will be its term. Looks a lot like this, except this is evaluated at c, and that's what the remainder will be, something in between x and c. Everything else is just like that, okay? Because you can't go any further with the Taylor series because the differentiation doesn't exist past that point. Okay. That's a remainder formula. Depends on what, there's some z in there that will be exactly what that remainder is. So here's the convergence for Taylor series, which I don't think you'll need to know, but just in case you do. If the limit of that remainder as n goes to infinity is 0 for all x's in the interval I, then the Taylor series f converges and equals to f of x. So even originally we said the Taylor series had the unlimited derivatives. This is if it doesn't have unlimited derivatives, it does have up to n plus first derivative. And here's Ricky. Okay. Pretty good attendance today. All right. And we just did Maclaurin series, as I showed it converges. I'll let you play with that if you want to. I'll let you see how it is. There is a Maclaurin series, like we did before. Only the odd powers of x, x over x to the first over 1 factorial, which is 1, minus x cubed over 3 factorial, plus x to the fifth over 5 factorial, minus x to the seventh over 7 factorial, plus x to the ninth, keeps on going. And you need to show that's true for all x. That's what they're asking you to do. And here's how you do it. The nth derivative of x is either the odd derivatives of f, okay, of n for any number n, it's n plus 1, okay? Those are all plus or minus signs, and the n plus first derivative, that's saying the same thing, isn't it? Oh, either or. Okay, that makes sense now. All the derivatives of f of x, if f of x is sine x, okay, they're either plus or minus sine or plus or minus cosine, okay. You know that the nth derivative of this is going of any value is going to be less than 1 for every real number c, because guess what? Sine and cosine is always the absolute value less than or equal to 1. It's got to be. Can't be anything else, because sine and cosine always stay between plus or minus 1. Okay? Therefore, for any x, fixed x, you can apply Taylor's theorem and determine that this. So you go back to Taylor's theorem and we didn't do enough on Taylor's theorem to do all those steps, but that's there. So that's how they, from the discussion regarding the relative rates of convergence, which we really didn't talk about, you can follow up and see this. I just wanted to show you these. Okay. Now this is indicating something, okay? When x is equal to, when you just do the first term of the Taylor series, that's just going to be x. Well, the sine functions like this, as I pointed out before, in this very narrow range, that is very close to the sine function, the identity function is. You do one more term to it, and now you've got a cubic function that fits really nicely here, so you've expanded the range over which that's really, really close. Then you do a fifth function, and remember all these have to be odds, and sine is odd, so that sort of makes sense. So now you've got a function that goes like this, this. So now everywhere between here, it fits incredibly well. The seventh function, when you include that one, now you get one that fits between there and there incredibly well. And you just keep on going. Now, The deal is, though, if you'll notice, past that point, things diverge really quickly and badly. So you can't say, oh, this will always work. It has to be an infinite series for it to be for all things, because you have to keep going. If you stop too soon, you're going to get some really major differences somewhere out here. It'll be great in between there. I mean, really, really good. But somewhere out there, it makes no sense at all. So don't think you can abbreviate a Taylor series and get too far. You have to know where you're doing. If you're doing a value that's way out here, you're going to have to do a lot of terms for it to fit way out here. Okay? If you're doing a value in here, it's going to convert really, really quickly. You won't have to do probably that many terms. Now, of course, calculators, computers do them really, really quickly. Okay. So here's the quick and dirty guidelines for finding a Taylor series. Differentiate f with respect to x many times, evaluate the derivative at some value c. Now, if there's a Maclaurin series, it's at 0. The Taylor series is some value c. But keep that c the same, okay? Do a bunch of derivatives and evaluate it. Try to recognize a pattern in these numbers. If you see after 4 or 6 or 8 repetitions of this, you start to see a pattern, then try to recognize that. Use the sequence developed in the first step, okay, to form the Taylor coefficients for this representation, knowing that after n factorial, this, whatever this is doing, especially if it's staying between some fixed limit there, like sine and cosine, say between plus or minus 1, then this is going to win big time after a while. Determine the interval of convergence for that resulting power series. We haven't been talking that much about it, but within that interval of convergence, determine how this series converges to f of x. And I don't want to say generally it will, but I want to say that. I can't say it because that's not necessarily true. But now, what do we mean by the binomial series? Anyone know? Binomial series. Something, I think probably Isaac Newton, again, was one of the first ones to really do much investigation of it. Before I say too much, let me turn to it. Yeah, it doesn't mention that. Before presenting the basic list of elementary functions, you'll develop one more series for a function in the form of f of x is equal to 1 plus x to the kth power. That's the binomial. This is a binomial raising it to a power. Okay? And if you think about this, you've done this or something pretty close to it many times. Pascal's triangle came pretty close to doing this type of thing. But that's the binomial series. Let's just see how they do example 4 then. So if you take a derivative of this with respect to, well, this is the function, okay? And f of 0, since you're doing a Maclaurin series, that's what you go to. F of 0 then would just be 1, okay? F prime would be k times that to the k minus 1. And f prime of 0, when x equals 0, x equals 0, that would be just k. Okay? Okay? F double prime would be k times k minus 1 times x plus 1 to the k minus 2nd. And at x equals 0, that becomes k times k plus k minus 1. Okay? And I think you see a pattern forming here. The third derivative, you see what it is. It's at 0, that would be k times k minus 1 times k minus 2. And you keep on going, and you just increase the k's, the products, k times k minus 1 times k minus 2 times k minus 3. and on up until the last one, whatever the last one you're going to take, the nth one, which produces a series, okay? The Maclaurin series, let's go back to it. It's alpha 0, that would just be 1, and then the next one would be k times x. Let's see, k times x, and the next one would be k, where is it? Yeah, k times k minus 1 times x squared, and that's what this one is. And you just keep on going until you get the nth one out there, and it keeps on going. By the ratio test, which we didn't do, you can conclude that the radius of convergence is 1. You got to be within that, okay, for it to converge. So the series converges to some function on the interval. It doesn't include the boundary 1. It's just within that boundary, minus 1 to 1. Okay. Now, here are just some of the power series for some elementary functions. 1 over x, guess what? You do it on your calculator, it's not telling you, it's not dividing 1 by x and then spitting out an answer. It's doing a Taylor series or Maclaurin series on that. And it's doing it really quickly. 1 over x plus 1 would then be this one. It's funny that would be a more complicated one than this one. This one's very straightforward. Log x, there it is. Okay? E to the x, they call it the natural base for our number system. Look at that series. 1 plus x squared over 2 factorial x3. It's just such a, what you say. Now, the funny thing is, the sine function never related to e to the x, but skip the first term, that term's identical, skip the next one, those are identical except for a sine, those are identical except, the next two. It's amazing. Cosine, by the way, starts with a 1 here, so it starts with this one, then the opposite of that one, the opposite of the next one, it goes up. Arctangent, even your inverse tangent functions, some of your inverse functions will have some very regular Taylor series arcsine. That would be this one. Notice that these are no longer factorials, nor are those. This is looking a little more like a factorial, but it's missing some terms. That looks like 3 factorial, but that isn't 4 factorial or 5 factorial. You're missing a 3 there. Okay, so here's you're missing a 3 and a 5. So rather bizarre, but true. And then here's your power series. Your binomial series, and that's pretty much exactly what we just saw. Okay. We're not going to do these, but you can combine things. Alpha of x is cosine of square root. Okay, they didn't do a square root series for us, but it's pretty close to this to the 1/2. Not quite, but you could fiddle around with it. And there's the cosine series that you could get right off the table, and replace x by square root of x and just basically take the square root of x. So that becomes x, this becomes x squared, and that becomes x squared. So that's all you do. You don't have to do anything fancy with it. Just take the square root of the x part. Not the whole number, just the x part. There it is. Okay. Whew. That's it. That's all of 9. That last was just exposure. I've already given you the test for this chapter, right? Or I didn't? Yeah. Thought I'd done that last time. Have I run it off yet? Sorry about this, folks. I thought I'd already done that. Let me see. Finding it is the hard part. No. Oh, wait. Of course not. Because this test covers some in Chapter 10 as well. I'm sorry. The only two sections you're tested on are 9.1 and 2. Sorry. It doesn't cover the whole chapter. That's why I haven't given you the test. Now, I don't know where I was thinking. So let's move on to 10. We probably aren't going to do nearly as much in 10 as we did there. In fact, we don't do 10.1 at all. Well, I'll do a PowerPoint show of 10.1 because you need to be at least aware of this, especially when you get to Cal 3. Y'all going to be taking that here this next summer, or are you going to take it back at home campuses? Home campuses? Okay. I think you need to see 10.1 anyway. You might need some of those series. I don't know for sure that you will. I kind of doubt it. I've very seldom used, well, I have used them some, but let's go from current show and let's do 10.1 because you need to at least see these. All right, conics and calculus, sort of alliterative subtopic, isn't it? Okay. What we'll do here, you're not going to be responsible for this on the test, but you probably do need to know it. Understand the definition of a conic section. Have any of you dealt with them before? No. Okay. Oh, you have. Okay. Analyze and write equations of parabolas using properties of parabolas. You've probably written lots of equations of parabolas using the properties. Probably don't even know what the properties are, but we'll get to it. Analyze and write equations of ellipses using properties of ellipses, and equations of hyperbolas using the property of hyperbola. I know you're going to need at least to recognize these in Cal 3, or at least the way I've always seen Cal 3 taught. So what are our conic sections? Now, if I were to ask you what a cone was, you'd probably describe something like that with me. But a cone is something like this, you know, the whole blue thing there. Not just half of that, like you use in chemistry lab, the whole thing. That's what a cone is. So a conic section, or simply a conic, can be described as the intersection of a plane and a double-napped cone. Double-nap means it's top and bottom. Okay? Double-napped cone, meeting at the origin, 0. Notice in figure 10.1, the four basic conics intersecting plane does not pass through the vertex of the cone. Okay? If it did pass through the vertex of a cone, you're going to have some lines in there. We're not passing through that. Now, if you pass parallel to the sheet of that, you get simply a circle. Down here are very small circles, up here bigger circles. You get circles if that plane is parallel to or perpendicular to the axis of the cone. Okay? You get a circle. I would have gone from here to here. Now take that perpendicular to the axis and tilt it a little bit either direction, and you get an ellipse. Okay? Whichever way you tilt is going to determine a major axis and a minor axis. But that slight tilting there of that plane will produce an ellipse. If you have that plane cutting through just the upper or lower half nap of the cone, then you're going to form a parabola. Okay? And parabolas only go in one direction, up or down, depending on which way that is. If, however, that plane cuts through both naps of the cone, then you get an hyperbola. Okay? Hyperbole never intersect. Okay? The two portions of them go like that. And again, we don't ever run the plane through the center, the vertex of the cone. So you get circles, ellipses, parabolas, and hyperbolas. So those are called the conic sections. Now, when the plane does pass through the vertex, the result is a degenerate cone. Okay? if that perpendicular plane passes through, you're only a point. Okay, that's the degenerate conic. Was a circle, but it got smaller and smaller radius until it became a point, and then it got bigger and bigger again. That's degenerating to a single point. Now, if you have that one that was forming this is hard to visualize, isn't it? It's going through the center, and it's cutting through in other words, take this one and slant it up, then it's only cutting through a single line of the line goes this way here and back that way down there. Okay. Get one that was forming a hyperbola, hyperbola, pass through the center, you just get two intersecting lines. Okay. I guess this is the one that did the parabola, but pass it through the center, and you just get a single line. Pass the one that was doing a hyperbola through the center, and you get a double line. Those are your degenerate conics. Don't worry about those. I don't think many things deal too much with those. Several ways to study conics. You can begin by, the Greeks did, by defining the conics in terms of intersections of planes and cones, like we just saw, or you could define them algebraically in terms of the general second-degree equation. All those conics are second-degree equations. Okay? Now, here's the most general form, ax squared. No, it's not. I wouldn't have put the coefficients like this, but they did. Ax squared plus bxy plus cy squared, okay, plus dx plus ey plus f equals 0. Now, these a, b's, and c's can, and these e's and f's, can have plus or minus signs. They can be positive or negative, let me put it that way, okay? And depending on what sign they have and which ones may be 0 or not 0, that determines which conic you have. However, the third approach, in which each of the conics is defined as the locus or collection of points satisfying a certain geometric property, they say it works best, and that's the one I think most people prefer to use. Visually, this is fine, okay? Algebraically, I guess this is challenging, but fine. The third, what is the definition of what makes that a conic? And here's what they've got. For example, a circle can be defined as a collection of all points x, y that are equidistant from some fixed point h, k. That locus definition easily produces the standard equation of a circle. X minus h, how far it is from that point, squared plus y minus k squared is equal to some r squared. R is that equidistance. Okay? That's exactly the standard equation of a circle centered at hk. Now, what are the features to be a circle? The coefficients of x, x's and y's are both squared, quadratic, okay? The coefficient of x and the coefficient of y must be exactly the same. Same sign and same value, okay? And it has to be a plus sign. So I said same sign. Should have said that separately. Same coefficient and a plus sign. Quadratic and coefficient of your squared terms are exactly the same, and there's a plus sign in between the two. Now they say that's the standard equation of a circle. And that's how we're used to seeing it. But to me, based on what they're going to do next and what you'll be doing in Cal 3, the better way to represent that would be this. I'm not going to do too much in this section, but I wanted to do this at least. Okay? X minus h squared over r squared plus y minus k squared over r squared is equal to 1. Divide everything by r squared, okay? And then you could actually, if you wanted to, write it as x minus h over r squared plus y minus k over r squared equal 1. I don't find that any better. I think this is probably the more acceptable form, okay? Only reason I do that is how they're going to represent the others later, okay? So get used to seeing it. Now, my plus there looks like a minus. That has to be a plus to be a circle, okay? So that's what it takes to be a circle. The coefficient, however you write it, the coefficient of your squared term, x and y squared term, have to be identically the same. In this case, it's actually 1 over r squared. 1 over r in parentheses. But they both have to be exactly the same and with a plus sign in between. Okay. Now again, why they jump to parabolas, I don't know. Ellipses make more sense here, but they do parabolas. A parabola is a set of all points x, y that are equidistant from a fixed line, which is called a directrix, okay, down here, and a fixed point, which is called the focus, not on the line, not on this line, the directrix, okay? So you have to have a line and a point. Any line and a point, then your parabola is going to be between those. Equidistant between the line, so of course the vertex of that would be actually equidistant between the point and the perpendicular point on the line. But any other point, this D1 must be that D1, this D2, that D2, this D3 must be that D3, okay? And so on and on, okay? That's what it takes to be a parabola. There's a definition, it's a pretty simple definition, and that's what it is. Now, let me just tell you something special about a parabola. And I bet you every one of you have used this special feature of it, whether you realize it or not. And here's the feature. If you had a single point of light right here, then what you would get from this, if this light reflects off, and this was a perfectly surface mirror of some nature, then the reflections would all come out parallel. Have any of you used a flashlight? Parabolic mirror behind, that mirror behind the bulb's on the focus. That's it. Now, it's not perfect. Why? Because the bulb is a perfect single point of light. Okay, it's fuzzy, so the edges get fuzzy. But any of you ever use a disc, television disc? Yeah. Okay, you use that. That's in reverse. All the rays coming in parallel from some satellite far enough away so they seem parallel, then they go to the focus. You know that little thing sitting out there? That's on the focus. Okay? So all those signals are being focused to the focus. Okay? So yeah, you use parabolas a lot of times. Okay? Your headlamps in your car, parabolic mirrors. The bulb is there, and you have just about a parallel beam of light coming out. Not exact, because it's not a point source. Some of them are off the focus. The light bulb is not completely on the focus. Okay, so here's the theorem 1, standard equation of a parabola. Standard form of this equation of a parabola with vertex hk, directrix y is equal to k minus p. So the distance from the h value to any the x That's, you know, this is the distance. Yeah. This is your x distance here. And this is from here to here, or here to here. I don't want to go into it. It just takes more time than we've got. But this is what it comes down to. Okay. Now, what I want you to notice here is this, and they say this is standard form. Notice one of the variables is to the first power, and the other variable to the second power. That's what makes it correct. That's what a quadratic equation, y is equal to some quadratic function of x. Those are always parabola, okay? Because your y is to the first power, your x to the second power. Now, everything else that's involved with it, yeah, that defines your directrix and everything else, okay? So, not going to get into any more than that, but that part. Now, I really want to write that a little simpler, but we won't get into that now. Okay. Then you can go to town with doing things like this. Completing the square will probably be involved in there somewhere. Okay. Yeah, completing the square. Okay. I won't work these problems. If you're interested in them and need them, you see them now, you can go back and retrieve them. Okay. Okay. All right. I don't know if I want to get into this part or not. A line segment that passes through the focus of a parabola and has endpoints on the parabola is called a focal chord. The specific focal chord perpendicular to the axis is the lattice rectum. Yay. One widely used property of parabola. There it is. Reflective property. In physics, a surface is also called reflective when the tangent line at any point to the surface makes equal angles to the incoming ray and resulting outgoing ray. The angle corresponding to that is called the angle of incidence, and the angle of reflection is one going out. And they're getting into a little bit of physics here, and that'll be fine. But another type of reflective surface that's formed by revolving a parabola around this axis, making a paraboloid, which you'll get to in Calculus 3, and putting the center of the light bulb on that, the rays all parallel going out. Or rays coming in parallel, all meet at the focus. Okay. So that's the reflective property of a parabola. P be a point on the parabola, tangent line to the parabola at any point makes equal angles with the line passing through P in the focus. And the line passing through P parallel to the axis of the focus of the parabola. Okay. Now, seems like ellipses should have followed circles to me. But an ellipse is a set of all points x, y, the sum of whose distances from two distinct fixed points called foci is constant. Okay? So if you have two fixed points here, and the sum of the distance between this point and that point and this point, that sum is constant. When you get over here, it's that distance plus that distance. Get over here, that's the same distance, okay? Get down here, that's the same distance. Over here, okay? Did any of you, when you were young, I know y'all may be way too young to remember this, ever see a toy called an Etch-a-Sketch? where you put a pencil or something, draw around, and get all these beautiful shapes. Kind of what you're doing here, only with one thing. Better thing would be if you had these points fixed and you had a string of length, something greater than that, then and you have it taut all the way around, you form an ellipse. The line through the foci intersects the ellipse at 2 points called the vertices. Line through the foci. Oh, okay. Line through both foci. These are vertices. That defines the major axis, the closest points, and that's the furthest 2 points away. Closest points are sometimes called the minor axis. Okay? So the chord joining the first axis is the major axis. Its midpoint is the center of the ellipse, right there. And the chord perpendicular to the major axis at its center is the minor axis. That's the closest point across an ellipse. Okay? Now, here's the standard form of the equation of the ellipse. Okay? Here's the key. The x's, both x squared and y squared, obviously. Okay? Their coefficients are not equal. This is over a squared, 1 over b squared. And this is why I like to write the circle in a different form, because this thing gives it to you. The larger number, a or b, that's going to define the major axis. So if a is larger, this is horizontal. If b is larger, then this is vertical. Oh, if a is larger, they flip them around. Okay. The variable that's in this form, x1, okay. This again is the center of the ellipse, not the focus, the center of the ellipse. X minus h, y minus k, that defines the center. And with that, both of those are squared. If the a is larger and it's underneath the x, then that's the major axis. If a is larger and it's underneath the y, that makes the vertical one, the major axis. Okay. I would have left these the same and said if b is larger, it's the major axis. The foci lie on the major axis, c units from the center. Okay, where c is the difference between a squared and b squared. Okay, so now you see why I wanted to write the circle the way I second said it, because that now looks more like this. Oh, always a plus sign in between the two. Always a plus sign in between. Okay, so let's go back to the parabola. I keep wanting to do it, and I didn't at the time. If you had divided this by 4, both of these by 4p, now you have something that looks like this, y minus k, and by the way, your hk here is your where do these give at? Yeah, the vertex, that is the vertex. It's not, excuse me. Sorry. I don't know why that comes up. It's the vertex of the parabola. Okay, here's a little bit of a difference here. Circle, HK is the center of the circle, so it's not on the circle at all. The center of an ellipse, not on the ellipse at all, but the center of I'm sorry, not the center, but the HK here on on a parabola is the vertex. It's on the parabola, okay? So, going back to this form, I guess I should have done it here, y minus k is equal to x minus h squared over 4p. Now that's not quite the form you'll usually find it, but to me that's a little bit closer to fit with the others. I don't want to get into that now. You run into it when you get into Cal 3 and you start talking about paraboloids. You'll find a different way to write it. But just remember, this is where this comes from. Okay. All right. I was starting to do. Oh no. Okay. Got to get out of this. Okay. Back to ellipses. So there's the way to write that. Okay. Now, and here is, you can visualize the definition of ellipse by imagining two thumbtacks placed at the foci, and then you draw your pencil. What's wrong with this picture is your line is going to get wrapped around the thumbtacks if you go around like this. But if you had a line that didn't wrap around, that would be exactly a string or whatever you have there. Okay, that's an ellipse. Okay, and you can fiddle with that and do all sorts of things. The key here, between your square terms, there's always a plus sign. If those have same coefficients, that's a circle. Different coefficients, that's an ellipse. Okay. Parabola, one of them's to the first power, one of them's to the second power. So if that was it, that would be a parabola, that would be a parabola. Either this or this. Okay. I'll let you play around with it if you want to. Okay. Reflective property of an ellipse. Let P be a point on an ellipse. The tangent line to the ellipse at point, P makes equal angles with the lines through P and the foci. One of the reasons that astronomers had difficulty detecting the orbits of planets or ellipses that the foci of the planetary orbits are relatively close to the center of the sun, making both orbits nearly circular. That's one of the things that differentiates a planet from some dwarf planets. Think your major 8 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Maybe another one out there they haven't discovered yet. It's not Pluto. Pluto has a very elliptical orbit. The others they're all ellipses, but the two foci are very close to the center of the sun. Not in the center of the sun, but very close to it. And therefore, they're slightly elliptical, all the planets. I don't know what it is for Pluto, but it's very far out. Pluto, sometimes it's actually closer to the sun than Neptune is, or other times way, way further. So it's not a planet. Okay. There are many other reasons, but that's one. Okay. So all the orbits are nearly circular, but none of them are exactly circular. The two foci are close to the center of the sun. They're probably all of them inside the center of the sun, but just close, but none of them at the center. Okay, to measure the ovalness of an ellipse, you can use the concept of eccentricity. And that just is a ratio of the C to the A, where A is half the major axis, basically. C is the center. Okay. So this would have a small eccentricity because your C is distance of the focus to the center is very small, and to the outside is fairly large. So this is a small, so this is nearly circular, but not quite. Small eccentricity. Here, the ratio of C to A is a bigger ratio, so a larger eccentricity. The eccentricity is always, I think, less than 1. Okay. Yeah, between 0 and 1. And these just show some of ours. Venus being the closest to being circular. Okay. Don't fault Mercury too badly. It's just so close to the sun that that's a much bigger number. But Venus to be the next closest planet to the sun and have that difference of an eccentricity is awfully close to circular orbit. Okay, we are pretty close to. Don't think just because Neptune is smaller than that, it's so far away. So its extremes are more than the extremes of Earth. It's just the ratio is still very small. Okay. Now, here's another interesting feature. The area of an ellipse is pi times A times B. Whereas, and it makes sense. For a circle, A and B are equal, and they are the radians. So that'd be pi r squared. So that makes sense, pi times E. Half of the major, what did I just call it, axis and half of the minor axis. Okay. Half the diameter is a radius. So that sort of makes sense. Now, another thing astronomically that this leads to is, have anyone of you heard of Kepler's 3 laws of planetary motion? Okay. One of those is the area that a planet, they have a name for it, covers in a time that it moves from point A. The areas are always equal. So when they're close to the sun, they're moving more rapidly far from the sun, much more slowly, but the areas of those sectors are the same. Okay, so that comes from this. That's one of the things Kepler, how he did it, I don't know. That'd be a good paper topic probably. How in the world did he develop those 3 laws of motion strictly empirically? I mean, you don't have any piece of paper to draw those things on. He did it, but he came up that the ellipses, the paths of the planets are ellipses, not circles. That was one reason Ptolemaic and all the others didn't work. Everything assumed they were circular orbits. They're not. They're ellipses. And then that the area of the ellipses was, of the sectors cut out in a given period of time are always equal. And the third one is the ratio between the, I don't remember now, the speed or the, it's a rather complicated one. But he came up with these, I think this is how it went. He went to Newton and said, can you explain why this work? I know they work. I developed them. They work for the planets, but I can't say why. And Newton had to develop calculus to explain that. That's one version I've heard. I don't know if that's absolutely historically accurate or chronologically accurate, but it was something that those were related. Well, this goes on into the area. I'm not going to get into all those. Okay. Now, hyperboles. Hyperbolas. Seems like they should be hyperbole. Yeah, but anyway, what do we have with that? Hyperbola is a set of all the points, x, y, from which the absolute value of the difference between the distances from 2 distinct points, called foci, are constant. The absolute value is constant. The line through the 2 foci intersect the hyperbola at 2 points called the vertices. So here we have 2 foci, but now the differences between the 2 points are constant. Not the sum, but the differences between the 2 points are constant. And so therefore, they go off like this. Foci in between here and vertices are there. Okay. So, and again, you can find eccentricity very similar to what we did before. Okay, so this is how they look. Think of your conic sections. That's same type shapes. Okay. The line segment connecting the vertices is the transverse axis, and the midpoint of the transverse axis is called the center of the hyperbola, just like we had center of the ellipse, center of the circle. You don't really have a center of the parabola, but you do of the others. Okay. One of the distinguishing features of a hyperbola that its graph has 2 separate branches that never intersect. Okay. Now, look at its standard equation. Again, the x's and now in this case, the a's and b's could be equal. The key here, I'm glad I closed the windows on my car. It's raining outside. The sign, the x squared and the y squared could have same coefficients or different coefficients, but the difference is it's a difference here, a minus sign. Okay? And if the plus is with the x, the transverse axis is horizontal. If the plus is with the y, it's vertical. Okay? So that's the key. Hyperbole have opposite sign on between the quadratic terms of the variables. So that looks just like that of a ellipse, except the ellipse will be positive there. The hyperbola will be negative. Okay. Now, another important aid in sketching the hyperbola is the asymptotes, because whereas you might think to yourself, was one of those, is that a parabola? If you just had half of a hyperbola, is that a parabola? Never. Okay? Because a parabola keeps getting further and further away. At some point, a hyperbola always approaches some asymptote. It's approaching some value here. Parabola is not. Okay. All right. The axis that's perpendicular to the, what they call it, the transverse axis, is called the conjugate axis. Okay. Conjugate, remember, x plus a, x minus a, that type of thing. The reason, some sort of connection there. So here are the asymptotes. They're related to those constants a and b. And it could be that the asymptote is the identity function and the opposite of that, if a and b are indeed equal. They can be. Okay. Okay. And the asymptotes, I don't know if you need all this. I don't think you do later, but the asymptotes, if you draw a rectangle that goes through the vertices of the 2 branches of the hyperbole, okay, and where this is h minus a k and h plus a k, okay, then do the opposite here and do h k plus b and h k minus b here. That forms a rectangle, and the asymptotes go through the corners of those rectangles. They are the diagonals, extensions of the diagonal of that rectangle. So you can play around with that if you want. But that's standard form. Okay. And there's lots of things you can play with. You can start with the center and draw your asymptotes from there. Okay. Eccentricity defined the same way as before. All right. That's it for 10.1. You're not responsible for that on the test. I mentioned, let me cover another couple of people. Hypatia, a famous Greek, one of, if not the earliest woman to be recognized as a brilliant mathematician. Not that she was the first, but the only one recognized. There was a guy named Apollonius. You can read this. But anyway, she wrote a text on the conics of Apollonius. Had a very tragic death, if I remember it correctly. I think you can read about it if you want. I don't need to go into that. A couple pages over, you see Nikolai Copernicus began to study planetary motion when he was asked to revise the calendar, and he determined the Earth wasn't the center of the universe. Unusual situation here. Copernicus was actually a monk, and basically the church was the center of learning in Europe, in Western Europe at the time. So, of course, if anyone was asked to do anything that required education, you had to go to the church, so he went to the monk. Well, he determined all these things, but he couldn't publish them because the church, the Pope, and the Hachos believed the Earth was the center of the universe. So to gone outside that, he would have been outside the church. But he found out it was true, but he had direct, specific orders. No one could publish his work until after he was already dead, because he didn't want to be made dead too soon. Okay, so later, people like Galileo, who read about his works and stuff, and said, yes, he's absolutely right, then they got put under arrest. Okay, so it's pretty interesting there. So there's a blurb there, there's further information there, lots of things you can look. Even though we're not covering it, you can read about. You can do your paper on anything there. Okay, before we leave, here's another, Caroline Herschel, first woman to be credited with detecting a new comet, was an English astronomer, a female English astronomer named Caroline Herschel. During her life, she discovered a total of 8 new comets. Okay. So anyway, we're not going to do those, but those are all connected. All right, so let's move on to this you are responsible for. So let's, this is where we pick up again. That probably spent way too long on things you're not going to be tested over, but those are pretty important things I thought you might need when you get into your upper levels. One of these days, the PowerPoint will open. I take it. Yes, here we go. All right, we are responsible for this. So this is where we pick back up. Slideshows are over. Now we're back to the real stuff. And how are we doing on time? We missed when we usually take a break. Does anyone need one? I have noticed a couple of people had to get up. Anyone need a break? Let's do it quickly. So let me pause here. 10.2 we are covering plane curves and parametric equation. If you'll go back and check the course description, parametric equations were one of the things mentioned. Conic sections were not mentioned, but plane curves and parametric equations, or at least parametric equations, were. All right, now what in the world do we mean by this? Our objectives here: the sketch the graph of a curve given by a set of parametric equations. What do we mean by parametric equations? That will be probably the first thing. We'll eliminate the parameter in a set of parametric equations to get them into more standard type form. we'll find a set of parametric equations to represent any old given curve, or at least some given curves, and we'll understand the two classic calculus problems, tautochrome and pachistochrome. I can't even pronounce them, much less do too much with them. We won't do too much with those, but at least introduce you to them. All right. Now, let's consider the path followed by an object that is propelled into the air at an angle of 45 degrees. Okay? Propelled into the air. At an initial velocity of the object is 48 feet per second. Okay? The object travels a parabolic path given by this equation right here. You say, where in the world did that equation come from? Well, we're not going to go into all of it, but just know that is the equation that it follows. Okay? I'll give you a little bit of the rationale for it, but just a little bit. There is a concept buried in here, because this is in feet per second. There is something in here that has to do with 32 feet per second squared, the acceleration due to gravity. It's not obvious how it's affected here, but the combination of that and the initial velocity of 48 feet per second, that's where the 72 comes from. The minus comes from the idea that the y is decreasing always, okay? Because gravity is pulling downward always. So you don't need to know why, but this is what you have. Because it's a angle of 45 degrees, initial, that's the projectile's initial angle, and the initial velocity is 48 feet per second squared. 48 feet per second. This is getting into some stuff I hope you picked up the trick. The x component of that velocity vector, because that's 45 degrees, has to do with the cosine of 45, right? The hypotenuse, which is the 48 feet per second, is the cosine of the angle, 45, is equal to the adjacent side over the hypotenuse, which is 48. Okay? So let's get that down. Let me get my pen. Where's my pen? There it is. Okay. Get back to black here. Okay, we just said that the cosine of 45 degrees is equal to the ratio of the x component of the velocity, let's call it v sub x, divided by 48, which is the total. Okay? Now, what is cosine of 45? Square root of 2 over 2. There's the square root of 2 over 2 is equal to v sub x over 48. Okay? Well, then the v sub x, the horizontal component of the velocity, is equal to, that must have been a bright thing to say, 24 times root 2. And there's your 24 times root 2. So your x component of velocity, your x displacement, is that constant component, x component of velocity, 24 times root 2 times however long it is. So that's the x component of your displacement is that constant x velocity, because there's nothing changing that, times the amount of time. So that's where that equation comes from. Okay. Now, the second equation is the fact that 1/2 is the acceleration, which is the 32 feet per second squared, and it's always downward, so that's where the minus comes from. So minus 1/2 of 32 is 16 times t squared plus the initial velocity in the vertical direction, which is a positive because it's fired upward, or at an angle 45 upward. Well, that's also, the y component is also 24 times root 2. Same reason, it's just the sine of 45 is the same as cosine of 45, it's root 2 over 2. So that same thing, so that times the t, okay? So that then gives us these two parametric equations for the motion of that projectile based on the independent variable t. X depends on t, y depends on t. These are parametric equations. Now, how did you get from that to this? Well, you could solve this equation for t, and that would be t is equal to x divided by 24 root 2, right? Well, if you multiply this by root 2 over root 2, then that would be, I shouldn't have marked those out. That's not what I intended to do. Okay. That would be, let me erase that while I'm here. T is equal to root 2 over 48 x. Okay? Then if you plug that in here, here, and there, you will come up with that equation right there. Minus 16 times 2 over, I don't know what 48 squared is, but 2 is root 2 squared, okay, plus, where is it, 24 root 2 times root 2 over 48x. Oh, and by the way, this has an x squared with it. Okay, because you're squaring both of those. Okay? I know this is ugly. Let me see if I can. I'll have to erase this thing that was crucial to it, but hopefully you see where it's coming from here. Okay. Here you see 24 times root 2 times 2. Root 2 is 2. That's 48. So that's where the x has a coefficient of 1. And if you do this part, this is minus 32 over 48 squared. Someone do that, and, well, square 48 and divide by 32. You're going to get 72. Try it. Anybody? 72? Yeah. See, that's where that comes from. With 48 squareds in the denominator, 32's in the numerator. Do that, and you get 72. So that's why I said it comes from the combination of half of 32 and the 48, and that's how it gets there. So this is written as one equation that's not intuitively obvious where it comes from, but when you write it as parametric equations, it makes, you know physics, it makes perfect sense where it comes from. And this is what we call curvilinear motion. Two variables for one position, one variable for time. I don't know exactly where the from curvilinear. It almost sounds like a contradiction. You think of this as being a curve and that being a line. It's not. But actually, this is a line and this is a curve. So, in a sense, that is curvilinear motion. Okay. All right. Now, to determine this time, you can introduce a third. Whoa. Okay. I'll even see where they mention time on this slide. There's a T there, it does, but all right. But then they start the next slide. To determine this time, I think there must have been some verbiage in the book that was there. You can introduce a third parameter T, third variable T, often called a parameter. By writing both x and y as functions of that new parameter t, you obtain then parametric equations. X is equal to 24 times the square root of 2 times t, which is the x component of the initial velocity, and that doesn't change, so that's a constant multiple of that. And the y component, which does change because gravity is pulling it downward while the initial velocity was pushing it upward, and that's where you get your parabolic action. Curved part of the linear part, okay? And this is the 1/2 the acceleration, which is always downward squared, so 1/2 of 32. That's your y component, which gets overwhelmed after a while by the acceleration. Okay. From those set of equations, you can determine the time t equals 0. The object is the point 0, 0. And you see from there, t is equal to 0, x is 0, t is equal to 0, y is 0. It's pretty obvious. But then you can pick any other time. T equals 1. The object would be at 24 root t. Root 2 is your x coordinate, and this would be 24 root t minus 16 would be the 24 root 2 minus 16 would be the y component. Okay, because t squared is still 1. Okay, and that's what we got here, 24 root 2 minus 16. And so, for this particular motion problem, x and y are continuous functions of t, and the resulting path is called a plane curve. You're staying in one plane, the xy plane, you're not moving out of it, okay? And it is a curve in that plane. So the definition of a plane curve is x and if alpha and g are both continuous functions of some parameter t. Now, for those people who are more physically inclined, it's real tempting to always think of t as time. It's not. It's not. It's just some parametric value, okay? The parameter t. They are functions of some parameter t on some interval I. Now that t has to be on the interval I. The I covers from t equals 0 to t equals 15, or t equals -3 to t equals +4. You wouldn't have -3 time, but it could be any parameter. Then the equations, alpha equal alpha of x t, y is equal g of t. X equal f of t and y is equal g of t. That would be your parametric equations, where t is the parameter that those two equations have in common. Set of points x, y obtained as t varies over the interval I is the graph of the parametric equations. Taking together the parametric equations and the graph are a plane curve denoted by capital C. Okay? And usually curves are capital C, whereas little c is usually, not in this text, but a constant or occasionally a path as opposed to a curve. But we won't get into that distinction now. Okay, when sketching a curve represented by a set of parametric equations. You plot the points in the xy plane, but you evaluate them at different different values for t. Each set of coordinates xy is determined from a value chosen for the parameter t. Pick a t, evaluate both x and y at the same t, there's your xy point. By plotting the resulting points in order of increasing values of t, the curve is traced out in a specific direction. This is called the orientation of the curve. Whereas just a parabola, like this, or whatever, it has no orientation. But when it's based on parametric equations, when t is increasing, the curve may be doing like this, it may be doing like this, it can be doing any number of things, but it is the orientation of the curve is from lower t to higher t. Okay? And you can't tell just looking at the curve which way that would be. So here's the first example. We are doing these. Sketch the curve described by these parametric equations. X is equal to f of t, which is t squared minus 4, and y is equal to g of t, which is t over 2, where t is anywhere from minus 2 to 3, inclusive. Okay? How do you think you would begin? Let's go on and draw the coordinate plane here. Not very good set of coordinate planes. That vertical is not very vertical, is it? So let's try that again. Something like that. So let's just tick off a few points here. Should be more evenly spaced, but they're not. Maybe not enough spaces, but let's see. Give me a T. Feel like a cheerleader.
0.
Okay, 0 would certainly be a good T. What would be your X? -4. And your Y would be?
1/2.
Second?
1/2.
I can't hear.
1/2.
Really? If T is 0?
Oh, sorry. I thought that was a 1. Yeah.
Okay.
My bad.
0. So there is a point where T is equal to 0. Okay? Give me another T. 1. Okay? What would your X be? -3. What would your Y be? 1/2. Okay, so that would be right there. Here's T. Get out of there. T is equal to 1. Okay, right about there. Give me another T. 4. Okay. What's wrong with 4? Oh, it's not in our domain, is it? So no 4. Give me another T.
Did we do -1 already?
-1 we could do. What would X be?
-5.
Second?
It was -3.
-3, okay. And what would Y be? -1/2, right? So there's your T is equal to -1. Okay? Give me another T. Anybody?
2.
Second?
2.
2. When T is equal to 2, what's your X? 0. What's your Y? 1. Right there. There's T equal 2. Give me another T. You got 2 more you could do. 2 more easy ones. An infinite number you could do. 3. Okay, when T is equal to 3, what's your X?
5.
5. What's your Y? 3/2, 1/2. Something about right in there. Okay, one more. -2. What's your X? 0. What's your Y? -1, right there. Okay, so here's your curve. It starts here, increasing and stops right there. I shouldn't have overshot. It has an orientation in that direction. Okay? It's tracing along this path. Okay, I'll do like point 12. Is that a function? Not of y as a function of x, but it is a correct parametric curve of two functions, y is equal f of t and y is equal f of t and x is equal to f of t and y is equal to g of t. I will get it out in a minute. Okay? So, you cannot write this as y as a function of x. No, it's not. You could write it as x as a function of y, though. We could do that. But this is a correct graph, a curve represented by the two parametric equations this way. And those are legitimate functions. Okay. My nose is itching. I must be going to have company. Okay. They put a few more arrows in there to indicate the orientation. You can put as many or as few as you want to. At least one should work. Okay. Any questions on that? If you were to be asked to give that as a function of y, which is legitimate, it passes the horizontal line test. Functions of x would have to pass the vertical line test. So this would do. How would you do that? There's a couple of ways. One's easy, one's hard. Anybody?
You're talking about the vertical line test?
No. I'm just talking about how to write this as a function of y. You can't write it as a function of x. It fails the vertical line test. You can write it as a function of y because it passes the horizontal line test. So how do you write this as a function of y?
You can substitute 2y equals t, sub 2y into t squared in the top function.
Okay, say that one more time.
Subbing 2y for t in the top function.
Okay.
That work?
Right, okay, but say the first part one more time. 2y, is that what you... Okay, that's what I couldn't understand. Yeah, t is equal to 2y, exactly. T is equal to 2y, and plug that in for the t up here, and you get 2y squared minus 4, which would be 4y squared minus 4. Okay? And that would give you this function right here. Okay? Only that doesn't have an orientation. It doesn't stop. There's no terminal values. This one is. This one starts right here and ends right there. I drew it drawing past that. This doesn't. It starts here and ends right there. Without that. Okay. Yeah, that's exactly how you do it. Okay. They mentioned here under technology, most graphing utilities have a parametric graphing mode, and you can use that sometime to keep from having to pick points. All right. Well, let's see how they do it. I was doing it. Let's see how they do. There's erase my lovely drawing. And they like tables, so they do a table, set up a t, and then an x and a y based on those t's. And they were a bit less random about their choice of t's. They started at -2, -1, 0, 1, 2, and 3. A bit more orderly there, perhaps, but you can do it any way you want to. And then evaluate the x at each of those t's and the y at each of those t's, and come up with the ordered pair x, y, and plot those points. And that's the same ones we get. And notice they are going from this point to that point, stopping right there. It starts right there, goes to there, and stops right there. Okay. All right. Any questions? All right. Now, what we've been doing already is eliminating the parameter. Okay. Michael came up with the way to eliminate it in that last one. Finding the rectangular equation that represents the graph of a set of parametric equations is called eliminating the parameter. For example, you can eliminate the, this is the one we just did, okay? And that's exactly what we got. We chose to eliminate here, solve the easy one to solve for t, plug that into the more difficult one here, and then work it out and get x equals y squared minus. That's exactly what we did. Okay. Once you have eliminated the parameter, you can recognize that the equation y is equal to 4x equal 4y squared minus 4 represents a parabola with a horizontal axis and a vertex negative 4, 0, as shown here. But the thing is, this expression has no reason to stop here or anything else. That would represent a parabola that goes indefinitely. The parametric equations are the thing that restricted your t's to only start here and there. Okay. The range of x and y implied by the parametric equations may be altered by the change into rectangular form. That's what I was just saying. There is no stopping and starting there. In such instances, the domain of the rectangular equations must be adjusted so that its graph matches the graph of the parametric equations. Okay, I wasn't talking about that, but that's certainly true as well. Okay. Now, how about this one? Sketch a curve represented by these equations. It says, by eliminating the parameter and adjusting the domain of the resulting rectangular equation. That doesn't look like a particularly easy thing to do, does it? Oh, it's not too bad. How would you go about eliminating? Any ideas? Oh, it is worse than I thought. I'm down here blinded by the reflection of the light. Okay? It's worse than I thought it was, but it's still not bad. Which one would you say the one to use? The y? I agree with you. Even though this looks a little simpler because it only has t in it one time, this has it twice, this is still in a square root. And the way to eliminate it here is to square, okay? Anytime you square both sides of an equation, you may be introducing what they call extraneous solutions. So you may get some values there you did not intend. Here, if you're careful with this, you shouldn't, okay? So let's see what happens. How would you go about using the y? What would be the first thing you would do? Multiply by the denominator, is that what you said? Okay, that sounds like a capital thing to do. T plus 1. Multiply this by t plus 1. Okay, so that gives you y times t plus 1. And these t plus 1s go out, it's equal to t. Now what? It seems like a reasonable thing to do there. Distribute. Okay? That would be yt plus y equal t. Right? Now what? Trying to eliminate your variable, or not eliminate it. Oh, what was the term we were just using? Well, that's what they said. Eliminate the parameter, eliminate the t. What would you do? Get the t's together. Yt minus t is equal to, actually I think I'll do it the other way. Okay? I'll say y is equal to t minus yt, and now factor out the t. I can't talk. Y is equal to, wait, yeah. Y is equal to t times 1 minus y, and then divide both sides by 1 minus y. So that's what the t is. Goodness, I'm about to lose my voice. And basically, there's your parameter. Plug that in here. X is equal to 1 over, ooh, this is a mess, isn't it? Y over 1 minus y plus 1, which you could then do as 1 over square root of y plus 1 minus y. Yeah. Y plus 1 minus y. I can't read my own writing here. All over y. It doesn't write well down here. That's part of my problem here. That's all over 1 minus y. I'm sorry. That's really ugly. Okay. And here, the y's go out. Plus y minus y is 0. So this gives you x is equal to 1 minus y. If I'm not mistaken. Is that right? Can it be that simple? It's square root of 1 minus y, sorry. Because when you invert and multiply, I think that's what you get. Let's see. Example 2. Yep. What they do next is square both sides, which is such a dangerous thing to do. X squared is equal to 1 minus y. So y is equal to 1 minus x squared. So yeah. So I guess we could have gotten that doing this too. Square both sides here, and you get x squared is equal to t plus 1. No, I'm sorry. 1 over t plus 1. Yeah, it's still been messy. Okay. But that's what they got in the book. Now, squaring both sides really does introduce some possibilities for problems there. But anyway, that gives us a parametric equation. Book did it exactly the other way and got the same answer. So that would indicate it probably doesn't matter much. Okay? Now, notice one thing for certain. T has to be greater than -1. One reason is the -1 in here is going to put you dividing by 0, and a -1 in here puts you dividing by 0. So you've got to be on one side or the other of -1. They chose the positive side. So anytime t is greater, this is going to be a positive number. That'll be a positive number. So I think we'll be perfectly okay everywhere. And then squaring both sides is not going to hurt you because t is already positive. I don't know though. Well, we're not going to worry about it now. But there's your parametric equation. Y is equal to 1 minus x squared. All right. The only thing I would say to this, if t has to be greater than -1, let's just take -1/2. -1/2, that's negative, that would be positive. So y can be negative. But in this form, oh yeah, so I think we're okay. Yeah, y can be negative. I'm sorry, this is the one I meant to do. X, if you use t equal any value here, this is positive, that's positive, so x has to be positive. So even though this looks like a parabola, it's not. It doesn't ever have x less than 0. X always has to stay on the positive side. Okay. That's where you have to watch it for when you square both sides. Things like that could come up. So let's see how they did it. Let's see. Yeah. Begin by solving one of the parametric equations for t. For instance, you can solve the first equation for t as follows. Now, this is what I said I warned against. So squaring both sides may introduce extraneous factors. But we wound up having to square both sides later anyway. So by doing this, you get x squared to 1 over t plus 1. Okay? Now, inverting that, okay, t plus 1 is equal to 1 over x squared. Then subtracting 1 from both sides, you get t is equal to 1 over x squared plus 1. Then if you write this over common denominator of x squared, this will be 1 minus x squared over x squared. And this will be 1 minus x squared over x squared, would be t. Plug that into your first equation, which they don't, your other equation, your y equation, which they don't show here, right here. Already forgotten it. 1 minus x squared over x squared, plug it in here and down here. And that gives you 1 minus x squared over x squared over 1 minus x squared over x squared plus 1. Now, several ways you can go here. What I would suggest is multiplying everything in the numerator and the denominator by x squared. So that leaves you 1 over x squared up here, 1 minus x squared down here, and over here you get an x squared. And that, I think, let's see if that's what they do. They didn't say how to do it, but that's what you do. Multiply everything in numerator by x squared and in denominator by x squared. Okay? And that gives you, numerator, those go out, and you get 1 minus x squared over, okay, your denominator becomes 1 minus x squared in your numerator, denominator 1 minus x squared there too, plus x squared. And the minus x squared plus x squared goes to 0, and that leaves you simply 1 minus x squared, which is the same thing we got. Okay? So either way. But the place that you've introduced something that can't be, if you look at this, you think, that's a parabola opening downward from 1 down here over here. No, it's not. No, it's not. You can't be over here because of your restriction that t has to be greater than -1. Back here that you had to begin with, way back here that you had to begin with, t has to be greater than -1. There's a very real reason for that. It's obvious there. It's not obvious over here because you don't even see the t. But you could have gone back and looked at those and seen that that's where you would have filled this in. Okay. You couldn't come up with any negative x values basically because of this. Like I said before, that's positive, that's positive. Always, 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 x can't be negative. Whereas there's nothing in this form that would indicate that x couldn't be negative, because that looks like a perfectly good function. But the rectangular equation is defined for all values of x, but from the parametric equation for x, you can see that the curve is defined only when t is greater than -1, meaning x's here have to be positive. Okay? Positive only. This implies you should restrict the domain of x to the positive values as shown here. Now, when you plug in these values, and here you have to be pretty careful how you do it, how I would choose my t's, knowing that t has to be greater than -1. You can't plug in -1, obviously, that won't work here or here. So don't even try it. But you could plug in a 0 here, and that would give you 1, and plug in a 0 here for t, and that would give you 0. So sure enough, t equals 0, you're right there. Okay. And 0. T is equal 0 here. Make x equal 1. When x equal 1, y is equal to 0. So sure enough, you're at that point right there. So this is obvious why t has to be greater than -1. Here it's not obvious why x has to be greater than 0, but it does. Okay. Oh, and the function, that's what I meant to say before. We started here. We didn't come down and do a -0.75. I would have next done a t equal 3, because 3 plus 1 is 4, and that would be easy to do. This would be 1/2 then. Looks like that's a little above 1/2, but I'll let him get away with that. And here, when t is equal to 3, this will be 1/2 here. T is equal to 3 here, 3 over 4. Y value there is, oh, I'm sorry. Yeah. T equal 3, that is the right place for the x. So the x is 1/2. The y is 3 over 4, 3/4, and that looks a lot like that. So it comes like this, but it stops there. It does not include 1 now. Why does it not include 1? They didn't restrict that at all, did they? Oh, yeah. You can keep getting larger and larger and larger, and you'll never go past that. Notice here, -3/4 is here, 0 is here, 3 is there, 4 would be somewhere 5, 6, 7. Whatever it is, you're getting closer and closer, but never right the value there. That's why. Okay. Enough of that one. Let's see if they do anything. Okay. they're skipping example 3, so let's go back and do example 3. I think this is where we're going to have to do it. Now, how are we doing on time? We barely got time to do it. I think we do. By the way, for those who don't have a book, and I know many of you don't, you can go to larsoncalculus.com, not only see this example done, but you get to interact, whatever that means, do an interactive version of this type of an example. So here's what it says. Sketch the curve represented by x is equal to 3 times the cosine of theta, and y is equal to 4 times the sine of theta. Okay, and we're going to do this for 0 less than or equal to theta, and that's less than or equal to 2 pi. So one cycle of cosine and sine, and let's see where we get. Okay? So let's tick off a few points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Mine are not very evenly spaced. Sorry about that. Okay. Give me a theta. 0. Good choice. What's your x?
3.
Second?
Wait, your x.
Yeah, with theta equals 0.
It's
3.
3. Positive 3. Okay? What, oops, I shouldn't have done it there. I was looking ahead. What's your y?
0.
0. I did do it right. Okay, I knew I did. Okay? Give me another theta.
In degrees or
Second?
in degrees, right?
I can't hear.
In degrees
Since they give these,
or radians?
since they give these in radians,
Okay, 5.
okay, pi will work. What's cosine of pi?
0.
Well, nope.
-1.
Negative 1. All right. After a while, we'll get there. So x is going to be negative 1. What's your y be?
0.
0. Okay. Could it be? Are we right there?
Or
I don't think so.
-3 to x?
Oh, you're right. Negative 3. Okay. I knew that didn't look right. Okay. Because it's, yeah, you're right. It's negative 1, but then you multiply. Negative 3 is somewhere over here, not very nicely spaced, but negative 3, 0. Give me another theta.
Pi halves.
Second?
Pi halves.
Pi halves. What's cosine of pi halves?
0.
0. So x is 0. What's sine of pi halves?
1.
So y is 4 up here. Okay? You want to do another one?
3 pi halves. Wait, can we do that?
Second, 3 pi halves. What's the cosine of 3 pi halves? Ugh. Second, 0. And what's your sine?
-1.
-1. So that gets you down to -4 here. So it looks like we have an ellipse. If I had spaced my things better, it would have been an ellipse with a major axis on the y-axis and the minor on the x-axis. I'm going to change my spacing here a little bit. Okay, so that would have been the top one. Okay, yep, an ellipse of that. Oh, which way are we heading? Counterclockwise, right? Because 0 was here, pi halves was up here, pi was down here, 3 halves pi was here, and 2 pi would have been back at 0. So you're going counterclockwise around that. Okay. That was example 3. My ears are popping for some reason. Now, Oh, wait. It says sketch the curve represented by that by eliminating the parameter and finding the corresponding rectangular equation. We just plugged it in. We didn't do what they said. I wasn't paying attention. What can you do to help me pay attention? How could you write that in XY form? And we know already that's not going to be a function. It's going to be a relation. How would that work?
Solve for theta.
What was the latter?
Solve for theta.
Okay, you could. That would be fairly difficult. What is a little technique that might make it run a little easier? It's one I warned you about before, but we're going to do it again. Squaring both sides of both equations. So what does the top one give you? Equal what? 9 times cosine squared theta. And the bottom gives you? I can't read my writing. Okay. Cosine squared theta. God, I got a headache. Say again?
Is y sine squared or cosine?
Yeah, I'm sorry. Y is sine squared. I think my squared is right, yeah. Okay, but why would I do that? That just makes it worse, right?
You can get the cosine in terms
Yeah,
of
I'm sorry. I should have done something else.
you get the cosine in terms of like 1 plus sine squared and then solve for sine squared and then plug in
Yeah,
y over 16.
yeah.
Sine squared.
I think perhaps one other thing would be multiply both sides of the top equation by 1/9. Okay, and both sides of the bottom equation by 1/16. Right? And then add the two equations together. Sine squared theta plus cosine squared theta is equal to, where is it there? X squared over 9 plus y squared over 16. Right? Well, I have them in backward orders, but it's still true. Okay? Now what's that? That's equal to 1. So x squared over 9 plus y squared over 16 is equal to 1. And guess what that is? Say again? Not a circle. Would be a circle if these two were the same.
It's an ellipse.
Ellipse. Same as we got here. Okay, because it's a plus in between, that's standard form for ellipse. The major axis is 16. I mean 4. You know, square root of 16. You know, from minus 4 to plus 4. The minor axis from minus 3 to plus 3. Like that. So yes, that's an ellipse. All right. And then from that, okay, they did it a slightly different way. They didn't solve for theta, they solved for cosine theta and then solved for sine theta before they squared both sides. We squared both sides and then solved for sine squared and cosine squared. Same difference. Okay. Now, they have sort of a conclusion here that I don't see as quite that obvious, but they make it seem like it is. But let me write this for you so you'll do, maybe you'll see it is fairly obvious, but I don't know. Based on what we just did, I just erased what we just did because I didn't have room for it, but they said, using the technique shown in example 3, you can conclude that the graph of x is equal to h plus a cosine theta, and y is equal to k plus b sine theta. Okay? And if you go 0 less than or equal to theta less than or equal to 2 pi, one period around everywhere, there is an ellipse, trace counterclockwise, but now, because of what we just did, and this is where the sort of obvious but maybe not quite obvious thing comes from, if you subtracted h from both sides here, x minus h is equal to a cosine theta, and y minus k is equal to k plus, it's equal to b sine theta. And now you've got basically the same equation you did before. It looks like a not equals to sign. I can't get it to erase. Okay. That's just like we had before, except that now it's x minus h and y minus k, and you can do the same thing like the book did, divide by a and divide by b, or as we did, square them and then divide by the square root, but you have x minus h squared over a squared plus y minus k squared over b squared is equal to 1 from your, so now you have an ellipse centered at hk, not centered at 0, 0. The previous one was 0, 0. Now it's centered at hk. And again, ellipses have centers. They're not the same as the circle center. That's not where you measure your A and B from. They're measured separately. Well, no, you do measure A and B from there. But the down here it would be r squared. This is A is less than what your r would have been if that had been a circle, and B is greater because you have a major and a minor axis. Okay. So, we're about out of time, aren't we? Okay. So we'll begin next time on finding parametric equations, which will be this slide. Here's my pencil. And we'll begin on this page. It's bizarre. I've never begun on that page before. All right, homework exercises in this section. We made good progress here. Do any of the odds 5 through 21. They're all at Calc Chat. 13's at Calc View. Think you can now do any of the odds 23 to 33. They're all at Calc Chat. 25's at Calc View. And we'll hang on and do the rest of those next time. Okay. Now, just another little issue. I forgot probably about as many people here as I did at the beginning. This class, one of my best classes ever, have received one research paper. We're running out of term, folks, okay? Running out of weekends. I don't know when you want to work on yours, but try to get those done. All right? Good deal. We'll see you on Wednesday. Remember, I'll be around tomorrow morning, 10:45 to probably 2 or so. I may be on the Birmingham campus after